If you feed the machine a picture, then try to train it to update the same picture. So what would the machine do? The easiest way is to remember the input image, which is a place to store the image, and then output it. However, we don't want the machine to be so lazy. We want to make the machine really understand the content of the picture through some methods, such as the meaning of the mountains and the sun here. Then draw it again. Today, we will talk about a model commonly used in machine learning called the autoencoder. An autoencoder is a special neural network structure that inputs x and outputs the same x, marked with an x asterisk. In order to try to recover x, the network needs to extract as much useful information as possible from the input. Autoencoders can be divided into two parts. An encoder encodes the input, and a decoder restores the encoded information to the original input. In order to avoid the network is lazy, that is, the input is simply copied into the output, we will put constraints on the middle hidden layer. For example, the dimension of the hidden layer in the middle is relatively low, so that it can only retain a part of the information. That is the useful information that can mostly help recovery. Therefore, when we only use the encoding part of the autoencoder, the input x can obtain the feature vector of x with low dimension, that is, dimensionality reduction. Recent studies only use the decoder part to input some low-dimensional information, and it can also be used as a generative model to generate data that simulates nature. This video mainly revolves around the question of how does a autoencoder limit the transmission of information. Several types are introduced. The first one is the undercomplete autoencoder. To prevent simple duplication, we will reduce the dimension in the middle, that is undercomplete. Therefore, the model will try to capture the most obvious features. Then, the model outputs the X star that mimics the input and compares it with the original input X. For example, using mean square error. That is, for each pixel xi corresponding to x and x star, calculate the squared difference. Finally, average all the pixels. Get the loss function. During training, we need to minimize the value of this loss function. If it is only a reduction in dimension, even if it is reduced to one dimension, that is, there is only one value. So, in theory, is it possible to keep all the information? In theory, it is assumed that the intermediate values can be 0, 1, 2, etc., all the way to infinity. If each input x corresponds to a specific code, well, it seems to be easy to remember. Of course, the reality is that the model can't really be coded so accurately. In experiments, the model still had to learn something while training. Of course, this is just an empirical proof of the experiment. Moreover, we have to limit the model, especially the dimension of the middle layer and the number of layers of the network. Then, obviously, the learning ability of the model itself may also be limited. So, in addition to reducing dimensionality, other constraints can be imposed, called a regularized autoencoder. Regularization in machine learning is a very important problem, and there are many studies. It will not expanded here. The restrictions imposed, such as try to keep the vectors of the hidden layer sparse, that is, a large part of the dimension is zero. Under such constraints, even if the dimension of the middle layer is larger than the dimension of the input x, it does not matter because the actual non-zero dimension is still very low. However, this time the input is these dimensions, and the next time the input may be these few dimensions. This higher intermediate dimension is called overcomplete, which is the opposite of the previous said undercomplete. In this way, it is called sparse autoencoder, which is to keep the intermediate dimensions as sparse as possible. That is, add one more item to the loss function just now. A sparse indicator for balancing the feature vectors of the intermediate layers. So, how to guarantee sparseness? For example, you can use the L1 loss function. Also, minimizing it during the training will make it as sparse as possible. Here it hi refers to the feature vector of the middle layer. Though such a training, we can take out the part encoded by the encoder because it already has the ability to extract the value information of the input x. We can add a classifier to it. It makes it a classification model. In addition to these limitations, there is another model, denoising autoencoder. As the name implies, it is to remove noise from the image. First, we add some noise to a normal and intact picture, which becomes X noise, or remove some areas X missing. Then take these corrupted images as input X to the model. Then we hope that the model will be able to restore the damaged part after it understands the real content of the image. That is to say, compare the output X star with the original intact X to obtain the value of the loss function of the difference and try to reduce this difference. Let's think about it. Can the image really be fully recovered? For example, the two areas that were erased here. In fact, these nearby pictures are very correlated with each other. We humans can guess very well a sharp corner of a mountain top, a partial arc of a circle. So I also hope that the model can learn the mutual dependency information here, effective information as part of understanding the picture. Others, like latent variable autoencoder, that is, from a statistic point of view, it is assumed that the values of some features of the intermediate hidden layer are regarded as a kind of random variable, which conforms to a certain random distribution. For example, we assume that they follow a multivariable Gaussian distribution or normal distribution because such a distribution often approximates natural. Such assumption also limit the representation region of intermediate values, forcing it to learn. Well, this video introduces several basic autoencoders, all of which are input X or X noise, trying to make the model output similar X star through training. This forces the model to learn how to extract the most obviously useful information from the input. It's just that there are several different types when different constraints and challenges are imposed.